So I want to introduce our first speaker for this September ECSS Symposium. That's Mona Wong from the San Diego Supercomputer Center. Mona works in the Science Gateway area of ECSS, and she's been working with PI Michael Cianfranco on something called the Cosmic 2 Science Gateway. And so this is a science gateway that connects data generated by cryo-electron microscopes, which is quite large in scale, with supercomputing resources. And this has the opportunity to really transform this field, because you're bringing supercomputing to a group of researchers who are not so familiar with it, with the intent of, allowing them to analyze these very large-scale data sets. Mona's going to tell us a little bit about that work. She's reprising a talk given at PERC 17, but I think that given the number of people who could travel and who happen to be in Mona's specific session, I think this will be new information to a lot of people on the call. So with that, Mona, why don't you take it away, please?
Okay, thank you, Nancy. I hope you guys can hear me okay.
Yeah, sounds just great. Also, I'll keep an eye out, or Marcus will keep an eye out for background noise and mute folks. And if you want to type questions into the chat, I can field those for Mona, and we can also unmute when she's done speaking. So, thanks.
Okay, thank you, Nancy. And thanks everyone for joining this talk about our Cosmic Square Science Gateway that we build for the cryo-electron microscopy research community. This gateway is pretty unique. It's currently the only science gateway using Globus for terabyte-size data transfers. And I think most of you know what a science gateway is. I borrowed this definition from the SGCI. Basically, a science gateway is a website that allows a community to share resources of various kinds. I always like to start my projects by understanding a little bit about the science behind the gateway. Structural biology is a field that was born in the 1950s with the determination of the DNA structure by Francis Crick and James Watson. And contemporary structural biology emphasis is on human health and disease, and is devoted to understanding structures of macromolecules and assemblies, because they believe these large macromolecules, like proteins, carry out most of the cellular functions in our bodies. And currently, this field is undergoing a revolution. One of the reasons for this revolution is a technique called CryoEM. It's a microscopy technique where beams of electrons are transmitted through the specimen at liquid nitrogen temperature. And this technique allows for a more natural specimen that's not stained or fixed in any way. Recent advances in this technique has made atomic resolution possible, and now researchers are able to solve structures that were previously unattainable. And in 2015, Nature Method called CryoEM Method of the Year. So there are three main challenges facing cryo-EM microscopists, especially new researchers. First is handling of large data sets, which are essentially movies formed by sequences of images. And as you can see, a typical data set is in the tens of terabyte range. Now you may wonder, as I did, why they shoot the specimen for so long. It's because these microscopes are very expensive and the resource is shared. And so researchers typically shoot as long as they can during their allotted time to get as much information for their reconstruction as possible. Cryo-EM technique require reconstructions, and those calculations require tens of thousands of core hours per structure, which necessitate the use of HPCs with the added complexity of transferring large data to the HPC, and also learning job submission and queuing system commands. Now, lastly, many researchers are not familiar with using command lines, which is required to run the analysis job and to submit the jobs. Even for researchers who know how to use a command line, an easier data processing mechanism we think will be welcome. And so to ease these challenges, we created the Cosmic Square Science Gateway with easy point and click interface that can be accessed from anywhere. It's built upon the successful Cypress Workbench framework, and we have integrated the Globus service for secure user authentication and authorization, as well as fire and forget large data transfers. Now, the gateway is currently taking beta tester signups, so if you or someone you know might be interested in trying it out, please go to the URL in the slide and click on the beta testing tab at the top. And I'll talk a bit more about the Globus Auth and Transfer shortly. First, a little bit about the Cypress Workbench framework. It's the software that built a mature and very successful phylogenetic science gateway, which has been in operation for 10 years now with worldwide usage and an impressive nearly 1 billion jobs submitted. It uses the Java Struts2 model view controller framework, and the user interface is based on the look and feel of popular email clients. And gateway operators can configure software and parameters available to the end user, as well as job submissions to different compute resources through XML files. It's been very successfully adapted by the Neuroscience Gateway, and the paper we presented at PERC 17 goes into some more details on the modular architecture of the framework, including reference to the original Cypress paper. So I won't talk too much about these details. We've done quite a bit of work customizing the Cypress Workbench framework. First is the backend Python script, customized to handle the data format specifically for the analysis software used and to dynamically set the number of HPC nodes. Second, we wrote a new Java and Hibernate package that wraps the Globus Auth and Transfer API based on the Apache Struts2 framework used by Cypress. Now, this new Java package can be used by other science gateways with minimum changes. And currently, we're working on making the Transfer UI a bit more user-friendly. Now, originally, the Cypress handles file-based input data sets. However, CryoEM data format is a directory full of files, many hundreds to over 1,000 files, which meant that this directory has to be compressed into a single file for Cypress. Now, this compression, as you probably can see, is prohibitive for data sets in the tens of terabytes. So we had to add to Cypress the ability to handle the uncompressed directory of data files. And we're currently also working to finish up this feature. All the codes will be available via GitHub. Now here's the component architecture. I just want to point out a few things. Note the Globus Connect software on the user side. I'll talk a little bit more about this shortly. The Gateway VM software stack is Linux, Tomcat, MySQL, and Comet is the XC petascale HPC machine at SDSC. And the configuration allows Comet and the gateway to access the transfer data directly without having to move it around, which is beneficial due to the large data sets. And then Globus acts as the third-party transfer agent. Now, the gateway has fairly standard set of user data and task management functions. And a couple of things I wanted to point out. By using Globus Auth, new accounts can be created automatically. And for data uploads, small files can be uploaded via the browser, large data sets via the Globus Transfer, which I will talk about in a bit. And the gateway offers a commonly used CryoEM data analysis software named Relion that can do 2D and 3D processing. So when the user submits their Relion task, it becomes a job running on the Comet supercomputer. And when done, the user can download their results, including standard out and standard error. Now, our gateway's login uses Globus Auth mechanism for user authentication and authorization. Globus Auth is basically a federated identity management, which means that user can authenticate using different credentials. So like Exceed's credential, their own universities, Google, etc. And then Globus can link these identities together. Additionally, Globus Auth can broker authentications and authorization interactions between users. Between end user, their identity providers, resource providers, and clients like mobile and desktop and other services. Globus Auth is built on the industry standard OAuth 2 and OpenID protocol. It uses HTTPS for safer communication. And one important note, that Globus Transfer does require Globus Auth. I'm going to show some screenshots of our user login process using Globus Auth. First, the user comes to our site and clicks on the login button. And then the gateway automatically redirects the user to the Globus login page. And then this page can be scanned for a fee from Globus, if anyone's interested. Now, Globus displays a list of identity providers the user can authenticate against. So as you can see, that's a partial list. As I mentioned, Exceed and most universities. And once the user chooses the identity provider, the user will be automatically redirected again to that provider to sign in. And once their sign-in has been successful, Globus will automatically redirect the user back to the gateway where the user will be signed in, and new accounts will be automatically created if needed. Globus returns some user profile information to the gateway, like the username, institution, email address, and so forth. And additionally, Globus Auth also returns a short-term delegated access token to the gateway so that the gateway can access the user's data on their behalf, including checking the user transfer status. Now, adding Globus Transfer to our gateway gave us the needed ability to transfer terabyte-sized data reliably. It's a descendant of Grid FTP, for those who are familiar with that technology, and it's TCP-based. Here are some transfer speed numbers between PSC and SDSC. And here are some impressive numbers for the Globus Transfer service. What I thought was impressive is that their largest single transfer is 1 petabyte, and their longest single transfer is 3 months continuously. And as I already mentioned, it does require Globus Auth. Okay, so how does it work? I'll go into a bit of technical detail for those who might be interested in doing the same for their gateway. Globus works by transferring between endpoints, and there are currently over 10,000 endpoints. The source endpoint is the user server, which must have Globus Connect Personal or Globus Connect Server installed. The Personal is easy to install. I've done it on my laptop, and I've seen the demo for the server installation. It looks pretty easy too. It does require root on the server to do that installation. And one useful thing to note, you can install the Personal on your laptop or on your server if you don't need multi-user access. And then the destination endpoint is the gateway storage on the data oasis at SDSC. Now, in order for all of this to work with the Exceed community account mechanism, there is an initial setup. So for those who are unfamiliar with Exceed, a community account is a mechanism which allows individual end users of a science gateway to submit jobs to the HPC resources without requiring individual accounts for every user. So first, the Exceed security team issues a certificate for the gateway's community account. Then the SDSC admin creates a subdirectory on the data oasis endpoint for the community account. And then the gateway creates a subdirectory for each user under our directory and manages access to prevent one user from seeing other users' data. Then for each transfer, the gateway goes through a process called Endpoint Activation, which basically sets up the proxy certificate needed by Globus to transfer the user data to the Exceed endpoint. And Part of this process, you retrieve the activation requirement JSON document using the Globus API. Then you obtain the public key value in the document. That's the delegate proxy field. And then using the public key, create a delegate X509 proxy signed by the community account certificate. Now this activation is good for a preset duration, and during this time, multiple transfers can happen. When the activation expires, Gateway repeats the activation process again. And these activation steps are included in our new Java package. Now, each Globus transfer can be configured with some properties. And we have configured the Gateway transfer to use encryption and overriding existing files if the timestamp is newer. That's the sync level equals 2 setting. So after the transfer is submitted, Globus returns an ID, which can be used later to check on the status of the transfer. And your gateway will want to store this ID for later status check. Then after the gateway submits a transfer request, Globus takes over and the gateway is no longer involved in the transfer process. When the transfer is finished, Globus will automatically send an email to the user. And an important thing to note about checking the transfer status programmatically by the gateway must have a valid user credential. And this is the credential that the gateway got from Globus when the user first logged in through the Globus auth. So, however, large data transfers take a long time. So most likely the user would have either logged out or timed out in our case. So therefore the credential will no longer be valid and the gateway cannot use it to check on the user's transfer. So what we've come up with is that we, for the gateway, will programmatically check on the user's active transfer when the user logs in. And if the user is still logged in, then there's a refresh button on the UI that they can click to get the update. So I have some screenshots for our Globus Transfer UI. This page is still a work in progress and a bit overwhelming, I think, but it does illustrate the functions that are available. I'll first focus on the section in the red box where the user can choose their source endpoint where their data resides. In the blue box, you can enter a string to search for on the endpoint that are public. For example, your lab's endpoint set up via the Globus Connect software mentioned earlier. Then in the red box, you can choose endpoints that are yours, like your laptop. Once you click on the Add button, that endpoint will show up under My Endpoint list, where you can then use to navigate to the location of your data. This is the destination endpoint, which is the gateway storage on the Exceed resource. And this is where you specify the data for transfer. Notice that it's showing a list of my source endpoint directories specified in the path field above. Currently, you need to manually enter the path of the directory where your data resides on the endpoint. So if I add Cosmic2 in the path field, clicked on the list button, I'll get a listing of the subdirectories on source endpoint on my laptop. And once you navigate to the parent directory, you can select your data directory and click on the transfer button. And this will initiate the endpoint activation process I mentioned earlier with the certificates, and then request is submitted to Globus, which then takes over and communicates with the two endpoints to transfer the data. Now, this diagram shows the components involved in the Globus transfer process, with the source endpoint on the user storage and the destination endpoint on the gateway storage. Once the data is successfully transferred to the gateway, the user would typically create a task, and this involves three main steps: choosing the data for analysis, choose the analysis tool, and specifying parameters for the tool. And they can either save the task to run later or run it immediately. And here are the components involved in the job submission process. The gateway checks the data is there and submits the job to Comet. And there's a cron job running on the gateway VM, which will periodically check Comet for the status of the job. And when it's done, it will retrieve the results and update the gateway database. So for our paper, one of the reviewers asked what we learned from this process, and I thought a slide would be nice. I think this project required a strong team effort, from gathering requirements from the domain experts who provided the continued feedback and testing, to the Cypress team support for code development, and then the job submission expertise from the Comet admins, and then Globus documentations and personal help in answering questions during the integration. We'll be in beta release soon with currently 2 labs eager to be testers, and the PI has applied for additional funding to improve and maintain the gateway. And PI is also looking to partner with CryoEM facilities to stream data straight from the microscope to SDSC. And we would like to perform all analysis steps from micrographs process to 3D model on the gateway. And lastly, perhaps expand compute to other XSEED and non-XSEED resources. Now, this gateway could not have been built without a team of people. Our team led by the PI, Michael Cianfranco, and the Cypress team led by Mark Miller, and then the SDSC leadership for the gateway VM and storage support. And thanks Nancy as well. And then the free development support from both XSEED and SGCI. Thank you for your attention. Are there any questions?
Mona, thank you very much for a very nice, clear presentation. There's been some Q&A going on in the chat during your presentation. I think most of the questions are answered there. We have a large number of participants today. Does anyone on the list have a question? Feel free to unmute at this time and ask.
This is David Del Vento from NCAR. I have a question about a Globus, the implementation of the Globus transfer into the gateway. Well, as you said, thanks for a very nice presentation and very clear and impressive work. And I'm actually working on a similar project for a total different purpose. But the question is, you know, it looked like you were a fair bit, maybe even a lot of work on implementing that transfer into the gateway. And from a functionality basis, it doesn't seem very different than what the Globus interface on their own website offers. And I was wondering, you know, if, you know, why they took that choice to do it, or maybe if the work wasn't as much as it seemed from the talk.
Okay, I don't know if Chu-Han is on the line. He is the one who did the development. But I'll talk a little bit about it. I think there was some learning curve initially to understand how this will all work, in addition to the way, together with the XSEED community account restriction. And the Globus API is fairly well documented. So once we figured out what the steps are and what calls we needed to make, I think the coding is fairly straightforward. Now, I think when you asked about the Globus page, yes, Globus does have a page that will help the user do the transfer. So why did we do it from within our gateway? The issue is a couple of things. One is this community account. So in order for the user to transfer the data to the gateway, they will need permission. They don't have access to our gateway endpoint. We will have to do it programmatically from our gateway. And so we initially added the way to do it from the Science Gateway, the way to do it from within our gateway. But I understand now Globus has something called the helper page, which the other issue is on the original page, you can see both endpoints. So you can navigate around both endpoints. which was not desirable for us because we don't want one user to see another user's data. And so we had to limit that. But now apparently I just learned that they have a helper page that only shows one side, like just a user side, so that they can choose their data and navigate. And then once that happens, then the gateway can get that information and do the transfer. So we might be integrating that in. We'll talk to the PI and see what he thinks. But I think that's kind of why we decided to integrate the UI for the transfer into our gateway, those couple of issues there. Hope that answers your question.
Yeah, I'm Chunan. In addition to, technically, Globus, has provided, some like very useful tools, but this is, based on Python, implementation. So at that time, I also like, I also got like some Java snippet code, from the Globus team. I think Eric Blow, sent to me, for like some Java snippet code, but this is useful, So yeah, like Mona said, yeah, this is a completely like, Globus designed for the like RESTful API based, So yeah, you keep in mind, this is Apache Structure 2 framework, which means like Cypress is using. So that means, you also like think about how to manage, account management system, based on existing account system with Globus authentication, This is, I think, sometimes tricky and then, harder part, So the rest of thing is, Globus guys, whatever, if you have some, something like, issues come up, so Globus guys are very, responsive, to help us in that case. So I really appreciate, Globus guys' help, at that time. So, okay.
David, I'm not sure if that answered it for you, but thanks to Mona and Shunhan. Mona, if you could stop sharing your screen right now, we'll get our next, thank you very much. And Damon, can you start sharing yours? Should be pretty clear just at the bottom of the Zoom window here. Well, oh great, yeah, that looks terrific. Thank you very much. Mona, I had one more question. If you're looking at expanding to other labs and other user groups with the Cosmic 2 gateway, how do you envision the data transfers working in kind of a more expanded way?
Right. So one of the things that Mike, the PI, has been thinking is to use AWS cloud services. Globus apparently have custom endpoints for the AWS as well as other, I guess, other organizations or institutions. So that's a possibility that could open things up for some users. And I think Mike is on the line. I don't know if he also cares to respond to this question.
Hi, yeah, I'm here. This is Mike Cianfrocco. Just to follow up, yes, we're thinking about how to scale up mostly the data storage end, which means connecting to maybe AWS or Google Drive or other sort of cloud providers. Again, with Globus, it's a really convenient aspect of Globus that they can connect cloud storage to endpoints such as the SDSC endpoint that we're using for the gateway.
Great, thank you. Thanks very much for joining too, Michael. Nice to have you on the call.
Yep.
Okay, great. So I'd like to move on to our second speaker now for this month's symposium. So Damon McDougall is from TAC, and Damon he's very recently joined the ECSS program, I would say within the last 6 months. And he's definitely had the honor of being the quickest person to join ECSS and offer to give a symposium talk. So I'd like to thank him very much for that. So we've got a similarly named but very different activity here. So we had Cosmic 2, now we have Cosmos++. And so this talk will be describing experiences porting this astrophysics code that simulates black holes onto the new Stampede 2 KNL architecture. So Damon, thank you very much for agreeing to speak, and please take it away. We can see your slides just fine.
Okay, thanks, Nancy. Can you hear me?
Yeah, your audio is coming over great. Thank you.
Okay. So this talk, I hope, will be accessible to you. The main idea is that I'm just going to share some of my experiences trying to optimize a PI's piece of software for Stampede 2. The code itself is written in C++, and there's often some considerations that you make when executing some optimization strategy, and coupled with software design. So I'll talk a little bit about both of those. So just as an overview, we'll talk about the scientific context, what the software actually does, and what the PI's research is about. I won't spend too much time on that. It's just to give you some motivation. And then we'll go through a couple of examples that I think stand out as key targets for optimization. We'll interleave those with some software design considerations, which are actually quite basic, but it's useful to have those and see them. And then we'll end with a summary. So the context is there's a debate about how to represent viscosity in the modeling of black hole accretion disks. So you can either parameterize the stress. The viscosity can take the form of a parameterized stress, or you can have it be driven by turbulence. The win of parameterization is that it's cheap to simulate. The downside of the full turbulence-driven solution is that it's not cheap. The difference between these two is not entirely well understood, but there's a paper by Pessar in 2008 that has a quantification of the difference. And as far as the PI knows, as far as the PI is concerned, or to his knowledge, there is only one study that made a direct quantitative comparison of these two using the same numerical code. So the goal of the PI in his science project is to extend the work by Reynolds and Miller and O'Neill to include a fully relativistic treatment of the Navier-Stokes equations. And the hope after that is to then capture the effects of strong gravity close to a black hole. So that's the scientific context. I'd offer to answer questions, but I know nothing about this, so I'm going to defer all of the scientific questions. But if you have questions about any of the optimization or coding strategy, we can talk at the end. Okay, so what does the software do? The software is discretized, basically discretized relativistic treatment of the Navier-Stokes equations, which is just a PDE. It's non-stationary, so there's a time stepper. The spatial discretization is some kind of finite element type discretization with an adaptive mesh treatment. And because it's a nonlinear system, there's a nonlinear optimization scheme inside the time loop. And the infrastructure is all C++ and MPI. Okay, so the situation is that the PI had already made an attempt at hybridizing their code. So OpenMP plus MPI. The resulting attempt didn't scale too well on Stampede 2. We do recommend, for running effectively on Stampede 2 or any KNL system, is that you implement a hybrid OpenMP MPI solution with maybe one is probably not enough, but at least 2 MPI tasks per node so that you can saturate the network hard, and each of these MPI tasks owning 64, 32. Essentially, the number of MPI tasks times the number of OpenMP threads is roughly 64. We also recommend contiguous stride 1 memory access, so you're not jumping around in memory. You're taking advantage of data locality. We also recommend you take advantage of the super wide registers on the KNL cards, KNL CPUs. And using the Intel compilers, you can leverage those vector registers with the -X Mike AVX512 compiler flag. The other thing to note on the KNL chip is that there is a high bandwidth memory, roughly 16 gigabytes of high bandwidth memory. I can't remember the exact speeds, probably around 400 gigabytes a second, 300 to 400 gigabytes a second. So about 4 or 5 times faster than DDR. And there's general TAC advice at this URL here. So after I send out my slides, all these links are clickable. So if you're interested, you can follow up in your own time. And we recommend using MCD-RAM in cache mode, just because in SNC4 mode, it's confusing and difficult to get maybe 1 or 2 extra %. So, okay, so that's the context. So I'm given this piece of software. How do I do anything? What do I do? Well, assessing software quality, it can be tricky, but what is really helpful is at least some kind of build system, so some way to automate compiling source files into object files and producing either a binary or a dynamic library that I can link against. I don't care what kind of build system it is, as long as it's automated, it doesn't really matter. Also, some kind of test harness. Again, there are millions of those available and free and open source. As long as there's some way for me to automate some kind of regression test or unit test so that changes that I make, I can be confident that changes that I make don't affect or change what used to be a correct solution or what the PI thought was a correct solution. Once I have those things, I can profile and understand where time is being spent and what may be a realistic test, what the structure of the code, what piece of the code is being executed for a realistic test. On the Stampede, on all the TAC systems, we have an Intel license and we have vTune. So if you're running on TAC systems, you can use it and it's free to use. There's lots of different vTune options you can use to collect data, but a very nice analysis you can do is a hotspot analysis, which essentially just tells you how much time is being spent in each function so that you can then look at optimizing the function that is taking up most of your runtime. So the PI's initial attempts didn't scale well because the majority of his time in the OpenMP part was actually spent in KMP fork and join. So the conclusion I make there is basically the OpenMP, the loop he was parallelizing, the loop he was threading with OpenMP wasn't really doing too much. So he wasn't feeding the threads. Okay, so the end goal here is to hybridize his software and have something that performs quite well. But I decided to take a step back and ask the question, well, what does the serial performance look like if we just run on a single, with a single MPI task on a single core? What performance might I expect, or what performance do I see? So this is a screenshot from vTune, a summary of where runtime is being spent. So you can see, out of maybe 40 seconds or so, 6 of those, so what's that, maybe 15%, are spent in this get conserved fields function, and then we have, roughly 10% of our time is spent in computing POW, comparing strings, allocating memory, and some other stuff. Drilling down, you can then see vTune gives you this tree structure. You can drill down and see exactly how much time is spent in each function. And the tree structure denotes, so a parent is just a callee, a parent is a caller and a child is a callee. So the highlighted field is essentially what we're going to concentrate on. This is the function we spend most time in. And the children here, we'll focus on some of the children and their children and maybe some of their siblings as well. I'll do maybe 4 or 5 examples and then I'll stop. Okay, so if you don't know C++, that's fine. The idea here is the concepts, not the actual language. This function, getOpacity, is called by getRossMeanOpacity. And essentially, all it's doing is it takes a bunch of parameters. One of the important one is this bin center. It's an array of doubles. And all we're doing with this is, note that it's not a constant parameter. So the function is allowed to change this array so that the caller sees those changes. But all this function is actually doing, so there's some stuff here, but it doesn't affect the result. It doesn't affect bin center. All this function is doing is looping over it and then computing pow. So the function is only reading the contents of the bin center array. It's not actually writing to the bin center array. So this was the first mental hurdle I had to get over, was I'm expecting this function to change this array, and it isn't. And that's okay, and this is just general software advice. But there's a book by Scott Myers called Effective C++, and there are 3 others. And I really, if there's one takeaway from this talk, is that I really recommend that you read these books. He's actually quite a funny writer, despite them being software books. But I learned a lot about how to think about designing software for myself, but also for other people from reading these books. And one of the pieces of advice in his Effective C++ book is use const whenever possible. So the idea here is that this bin center parameter, this should read const vector double ampersand bin center. And the reason that we make, the reason to make that parameter a const reference is 2 things. The first thing is it tells me, the person reading the software, that the function cannot change the array. So I have certain guarantees that I can work with when working with the software. The second thing is that it tells the compiler to yell at you if you try to change it. The reason that's important is because if I'm trying to optimize something, and or I might change the implementation, and I decide to then write to that array, I'm allowed to do that, and the behavior might change for the caller. So if you prevent that from happening, you safeguard yourself from making an implementation mistake that you don't want to make. So this is not an optimization piece of advice. It's just a how do you stay sane piece of advice. Okay. So if you remember from the breakdown, so we're going to look at this getRossMeanOpacity function, which is the parent of this function, the getOpacity function. So getRossMeanOpacity calls getOpacity in this line right here. So the idea here is what's happening, we're allocating an array of size numbins, we set them to 0, and we pass that array to this getOpacity function as the last parameter, and then we just care about the first element, and we write the first element opac n, and then the caller sees the result. So we're allocating possibly quite a large amount of memory, and we only care about the first element. Really easy way to optimize this is to leverage a language feature in C++ called function overloading. That's not the only way. I just did it that way because if I change this function, the PI's code might break somewhere else. So I added an overload, and you can get rid of this allocation, and you can just pass a double to an overloaded version of getOpacity, and then you've elided the memory allocation. And if you remember from the summary, memory allocation was taking up 10% of our runtime. So that's a useful thing to do, is to elide memory allocations, if possible. Okay, this is a much more complicated one, but that's okay. I know it's a screen of nasty code, but that's fine. Let's just break it down. So we have a function called apply BC that belongs to this pole axis BC class, whatever that is. This parameter takes a non-const reference to a vector of doubles. So the more seasoned C++ people in the audience will probably realize that this is not a great idea, but I can explain. I'll explain why to those who aren't so seasoned. So the function does some initial setup, whatever that is, and then we allocate a vector of ints called opzone index. It gets default constructed, so the memory gets allocated, and then whatever. And then the second line, we call a function and then assign it to the thing we just allocated. So we're doing a memory allocation, and then we're doing a copy. So that's two things to note. The third thing to note is why would you write vector of int? Well, the reason you would write that is because your for loops over the elements of this index array look quite nice. So opzone index, for example, here, you can use the familiar array index notation, so first index, second index, third index. And for loops over those indices look quite nice. That's a reason why you might allocate memory like this. The thing to note is that this opzone index variable, it's only being read. So here we ask for its size, and here we just ask for elements of it. We don't actually write to it. And that's fine because it's a local variable, and so it would be deallocated at the end of the function. So you expect to only read from it. Another note is that I had to modify the PI's code to get it onto the slide. So there's other stuff going on here. This is not the whole picture, but what I'm showing you is the truth and nothing but the truth. It's just not the whole truth. But the takeaways are on the slide and they are accurate. Okay, so to summarize, we're doing an allocation that is quite nasty. We're doing a copy, and then we're reading from this index array. So how could we improve this? Well, I said I would explain why allocating vector is a bad idea. And the reason is because when you allocate an array like that, the elements of that array don't necessarily lie next to each other in memory. So for example, the inner vector is a contiguous array of integers, but the vector that holds those vectors, the addresses would be contiguous, but the actual elements of the inside array would not be. And again, for the outer one. So the outer array is an array of vectors, a vector of vectors of vectors. And the actual elements of those don't lie together, but the addresses of the arrays do. And if you remember, I said at the beginning, we recommend contiguous one-stride memory access. So you're not jumping around in memory. You want to take advantage of data that's close together. So the code that I just showed you allocates a non-contiguous array of ints, and then we copy it, and then we only read it. So one way you might optimize this is, if we go back, we might have this function here. This get opzone index function is just returning the structure we want to read. So we might instead implement this function here differently to instead return a reference to the data structure we're indexing over, rather than returning a copy of it that we then send over to this local variable here. The reason we might do this is because we then wouldn't need to allocate an array. Right? We could just ask for this thing and then dereference the elements that we need. It also elides the copy, so we don't need to do this we don't need to copy all of the elements of this array into another local variable. We can just have mfield store it and then just dereference what we need. And the reason that so I mentioned that this thing is we're only reading from it. That's crucial because if you want to write to it, you have to understand that returning a reference and then writing to it will change the stored memory inside this object. If you want to write to it without changing what's stored inside mfield, you would need to make a copy. But here in this case, we're just reading from it, so it doesn't matter. And the last thing you might do to optimize this is to rejuggle the data structure entirely so that we're not doing a vector, vector, vector. We just have a vector of, a much longer 1D array rather than a complicated non-contiguous 3D array. This is much harder to do, although the code I've showed you, it's not hard, but in other places in the PI's code, his MPI communicators were aware of this type of nested data type. So making that change is not an easy change to make. But at least I can communicate to him what the problem is and he can implement a solution that he's happy with. I realize I'm running on time. So what I might do is quickly go over maybe just one more example, and then I'll stop for questions. So I'll skip this example. The takeaway is that why allocate memory when you don't need it, but you've basically already seen that example you've already seen that takeaway in the previous example. I'll skip this example as well, and I'll do a much easier one. But the idea, again, more words of wisdom from Scott Myers. A really useful takeaway is to use objects to manage resources. I kind of hinted at that earlier with that mfield class, storing that index array. Make mfield responsible for managing the index array memory rather than copying it locally and doing whatever. And then mfield's destructor will responsibly delete that memory. Yes, one more example, the easy one. So we're going back to the first function we saw, which was this get opacity function. It's very simple. It's just a for loop, and each element calls pow. So I'm thinking, I'm looking at this pow call. What are the arguments to pow? I mean, obviously this code doesn't compile because I've removed all the setup here, but in my GDB session, this was an integer, and this was something like 3.5 or something. Not like recurring decimals or whatever. But 2 to the 3.5 can be rewritten as 2 times 2 times 2 times the square root of 2. It's not exactly the same floating point calculation, but it's the same mathematically. And the idea of writing it this way, so essentially we would replace pow with new times new times new over nu0 times nu0 times nu0 times the square root, whatever. Essentially getting rid of this pow call with square roots and multiplies. And the reason that's attractive is because the AVX 512 instruction set does not have, as far as I know, does not have a vectorized pow instruction. It does have a vectorized square root instruction, and it has a vectorized exponential instruction. I'm sure someone that's more knowledgeable than me in the audience could correct me if I'm wrong there, but as far as I'm aware, that's true, and that got them a good, non-trivial speed up. Okay, so I've shown you some optimization strategies and a very small amount of software design considerations using const and proper memory management. But what has this brought the PI? Well, the PI got to roughly a 30% speed up on Stampede 2, a 3x speed up on his laptop, probably for a different use case. And I really didn't have to do too much. Honestly, I just I spent a lot of time in VTune and honestly just reading their code and trying to understand what it was doing, and places where I could look to try and make things run quicker. The advice I've given here is fairly general. Your mileage may vary with it depending on your application. Also bear in mind that I certainly make assumptions about some of these optimizations. And so those assumptions, in particular, the examples that I glossed over, those assumptions may not be, they may be unsatisfiable. So the PI doesn't want to make that assumption, or it's just an unreasonable assumption to make. Maybe a memory footprint assumption or something. In that case, you can communicate those assumptions with the PI. Hey, if you make this optimization, this is what it gets you, but you sacrifice this. And then the PI can, and has done, taken that advice, and instead of implementing my advice, he's chosen a different approach that has a different set of constraints and assumptions. The idea here is that you won't get anywhere if you don't play around with your software and understand where it's spending time. And one of the things I learned throughout our interaction is how to communicate at the right level. I'm not an expert in his domain. He's not an expert in my domain. So there was some growing pains, but I certainly learned how to communicate some of those ideas more effectively. I'm done. So if you have any questions, I'll happily try and answer them.
Damon, thank you very much for an excellent talk. Lots of great advice for the ECSSers on the call. Let me open it up for questions. We have a few minutes. Nothing's come in on chat, but any questions from folks on the line? Yeah, I think you were quite thorough in your explanations, which was wonderful. And I also liked just kind of this generalized approach that you outlined for how to handle ECSS engagements, from the necessary things like the test harness and a build system, starting with profiling, finding out where the code's spending its time, and then really going back to the basics. And your collection of books made me think about opportunities to collect such things and put them on our staff website for ECSSers so that we can get to what's actually usable from a programming standpoint for these projects. So I thought there was some really good advice there. And also, how to communicate with the PI and team, because you're exactly right. They're experts in one field. Our ECSSers are experts in something else, and that's the whole reason for the program, is the coming together of those two areas of expertise to achieve something more. And so you demonstrated that quite nicely. So
thanks. Yeah, I mean, I feel like half the battle is just getting started, and if there's not some kind of build system and test harness, it's just much harder to get anything done. So I was really over the moon when he told me that was implemented, because it made my life so much easier.
Yeah, I've definitely heard from other ECSSers where that's not the case, and
right.
Even the ability to build the code is something that they've had to develop. Sometimes they end up with more expertise doing that with the PI, but the PI sort of understands how untransferable and unsustainable their current model is because of the ECSS association.
Yeah, I completely agree. I could spend hours talking about best practices in software engineering and version control, but maybe a different talk.
Yeah, thank you. I think you'd have several ECSSers agreeing violently with that kind of presentation. Well, one last chance for questions from the audience. Yeah, go ahead. Is that Mona?
Yeah, I just have a couple of quick questions. I don't know if you mentioned this earlier. Sorry if I missed it. Which profiler did you use, and how long was this collaboration?
So I'll answer the last one first. The collaboration is still ongoing. This is just what we've tried. I still haven't done the hybridization yet, and that's really what he wanted. And then the answer to the first question is, I used VTune because I was on Stampede 2 and it's free. But any profiler will work, as long as there's a tool that you can use to tell you how much time is being spent where. That's the information you need. So however you get that is up to you. gprof is an open source one, but yeah, we have VTunes. That's what I used.
Okay, thank you.
Sure.
Hi, I have a quick comment and a question. I thank you for the presentation. You showed a number of good optimizations, and the comment is that in general, with a higher language as C++, there's a number of things you need to watch out for in terms of performance. And the question is that vector of vectors. I was wondering if that's really necessary, and if maybe an array can be used instead of that.
So, good question. Vector, is that necessary? The answer is no, it's not necessary. I suspect the PI wrote it this way because then his for loops look like this rather than doing arithmetic inside the array index. You could do a vector of ints that's just larger that contains everything you need. And then your second question was, why wouldn't you just use an array? If I'm understanding you correctly, and you're talking about the C++ array type, that needs to be sized at compile time.
Oh, well, no, that's not quite what I mean. I actually mean that, okay, so C++ has a lot of very interesting features, and they're very convenient to use from a software engineering standpoint. However, from performance, they are not necessarily will give you the best performance. And I find it helpful to go back to the lower level C features in the crucial parts of the code. So I just meant a regular C array.
Okay, so I have a different answer to that question, which is that you should use objects to manage resources. A vector of ints and a C array of ints are basically the same thing. They're both dynamically allocated. The difference is that if you don't have enough memory, the constructor for the C++ version will throw an exception. Whereas in C, you are required to check the return value. And we all know how good we are at checking return values for malloc. So it's just safer to use the C++ type for an array. If it's just a simple array, there's nothing wrong with doing that. If you don't, you're responsible for making sure that when you throw an exception before you free the memory, that you have to make sure that you're not causing undefined behavior by throwing an exception in a destructor or not freeing the memory at all. This is quite a complicated question, which I'm happy to go into detail in, but I have office hours to go to.
Yeah. Okay.
Is that sufficiently?
Yeah, I think you're right. It's a complicated question.
Yeah. Okay.
Thank you.
Sure. You're welcome.
Great. Well, thank you very much, Damon. I'll ask both Damon and Mona to send me their slides. We'll post them on the website. And contact information for the speakers is also on the ECSS Symposium website. So you're perfectly free to send them questions outside of this hour. Appreciate both the speakers taking time to prepare their presentations and deliver such excellent presentations for us today. And hopefully see you all on the October ECSS Symposium.
Thanks, Nancy.
Great. Thank you very much, everyone.